I don't know if anyone has done this, but if you take that sunlight and you shine it through a prism, or you might see it reflecting maybe from a mirror or through your window, you notice that, well, the sunlight really isn't just white light. It's broken up into colors. And a huge example of that is something that you see during a rainstorm, right? Like a rainbow, breaking up all those different parts of the light. Well, if you look even closer, you might find some funny things. So if we look at this spectrum, this is the spectrum of the sun seen on the ground, you'll notice that some of the light isn't coming through. So you might wonder, well, why is that the case? Does the sun just not shine in that light? Is there something in the way? What is going on? So one thing that I forgot to mention in the beginning is I would like everyone to kind of be free to ask questions or interject comments as we go along. So I want this to be kind of a two-way talk. I don't want me, just sitting here and just blabbering on the whole time. I would like to have, some conversation, especially from the younger folks here who are students, or maybe those who are in college, or for those of you, this is, maybe it's, this is just a one-on-one for you, but that's fine. So I guess the question is here now is, why are these parts of the spectrum blacked out? What do you think might be the cause for that? Anybody have an idea or a guess? Yes, sir.
Something's absorbing those frequencies.
Yeah, that's exactly it. So something is in the way to absorb the frequencies. So what might be in the way? I mean, we have the sun and then we have Earth. What's in between those?
Atmospheric molecules.
Exactly, it's the atmosphere. So what's in the atmosphere? We have probably a lot of water, right? We have other different types of molecules. There's a lot of nitrogen. You have ozone, so you have absorption from that. Now, what about the atmosphere of the sun? Or does the sun have an atmosphere? It does, right? The sun has an atmosphere just like Earth. It's a little bit different. It's a lot hotter, but there is an atmosphere. And the atmosphere of the sun does a similar thing. It does some absorbing as well. Not as much as the Earth's atmosphere, but you can account a lot of these absorption lines from the atmosphere of both the Earth and the sun. I couldn't tell you which one's which, but the interesting thing is, if you've ever studied emission spectra or absorption spectra, every element and every molecule with different kind of vibration modes or rotational modes, every single one has a very specific pattern. Just like how everyone has a very specific fingerprint, every atom and molecule has a very specific type of light that they absorb or emit, depending on what kind of environment they're in. So if you went in the lab and you said, okay, hydrogen has this spectrum, you would go and you'd be able to find, the hydrogen lines. And then you go, okay, what does the spectrum for argon look like? And you might come in here and you'd find lines for argon, and so on. And you do this, and then you run out of atoms, and then you realize, okay, there's molecules that are doing some absorption, and so on. So there's a lot of science and chemistry that's actually going on in this picture that you might not have realized from the get-go. But as you know, for astronomy, we use light to study far, far, far away objects, different galaxies, other stars in our Milky Way, and so on. So light is a very important probing tool, and sunlight is definitely a part of that as well. Okay, so now that was all the visible spectrum. So let me introduce to you some of the UV spectrum. So in the background here, this is just our normal white light that we see here. You can kind of see a sunspot. But as you go deeper into the UV, you're seeing different parts of the sun's atmosphere. So what part of the sun do we see in white light, in visible light, that we're used to seeing? Yes?
The photosphere.
This photosphere, exactly. Which kind of makes sense, right? They kind of named it, what it's for, the photosphere. It's the sphere that you see light from. But as you go into the UV, I can't remember the exact wavelengths, but it basically goes down to something on the order of tens of angstrom, where an angstrom is, a tenth of a nanometer, so something very small. So yes, go ahead.
These colors don't really mean anything.
They don't. They're just ways for us to differentiate. So they're false color. But you can kind of think about it. Suppose we had a lens, an eye that could see UV and could differentiate colors. You can kind of imagine that maybe this would be something you can see. I don't know. But it's false coloring, definitely. But this back one this is real color. But all these other ones are false color. And they choose them such that they're contrasting against each other so they can see different features. So as you can see in here, some of these you don't see any prominence loops. You might see maybe some active region. It looks like there's a sunspot there. But in this wavelength, you can definitely see magnetic field structures and so on. And same with here. So just depending on the different wavelength. But the point that I want to make is, as I said, the different UV light looks at different parts of the atmosphere. So the next thing that I kind of want to impart on you is that, okay, so the sun is a hot burning ball of hydrogen. And if you imagine, standing by a campfire, your intuition tells you the farther away you step from the campfire, the colder you feel, right? But with the sun, it's not really the same. So if I'm on the photosphere, do you remember how hot that is in Kelvin? Does anybody know that number off the top of your head? Yeah.
700 degrees?
It's about that, yes. Is that?
I was going to say 6,000, but yeah.
Yeah, exactly, yeah. So about 6,000, 5,700 Kelvin. So it's pretty hot, It's a pretty hot campfire. But if I was to step back, maybe tens of miles above the surface, would you expect it to be colder or hotter?
It's actually hot.
It is actually hotter. So it's kind of against your intuition, right? Because if you imagine a big ball of fire and you step away from it, you would guess it's getting colder. But actually, it's getting hotter. And what layer of the sun are you getting into as you go into the upper atmosphere of the sun? Exactly, the chromosphere. And then you have the farther part of the atmosphere, which you see during like a solar eclipse, which is the corona, right? So as we have found out, the corona is actually millions of degrees Kelvin hot compared to thousands of degrees Kelvin at the photosphere. So as we're going into deeper UV, so that is to say higher energy UV, we're probing hotter temperatures, if that makes any sense. So it's kind of like saying kind of a cold fire is red, but a very hot fire is blue. It's kind of the same concept. The hotter you fire, the more blue it is. And then you can get to the point where you're getting in UV, and the deeper the UV, the hotter yet the fire. So what this picture is showing is we're probing higher and higher layers in the atmosphere of the sun as you get out into the corona. And these first couple are an important region, what they call the transition zone. It's kind of the zone where the increase in temperature just skyrockets. And that's where they think a lot of interesting physics is happening. Because currently it's not understood why the corona is so hot. So if anyone here knows the answer or might have any guesses, you might get a PhD, or not a PhD, you might get a Nobel Prize. You probably get a PhD too, If you get a Nobel Prize, you might as well, right? But you'd get a Nobel Prize for that. That would be, that's on the list of trying to figure things out. But currently, some of the guesses are, maybe it's nanoflares that are happening, very small flares that are just popping off very fast, very frequently. Or it could be magnetic reconnection. That's kind of like the hot topic of the past decade, is magnetic reconnection, which is basically converting magnetic energy into kinetic energy. So they're thinking, well, maybe that's where the energy is coming from, because the energy has to come from somewhere. Heat is energy, so where is the energy coming from? That's kind of what they boiled it down to. But they still don't really know. They can't put their finger on what it is. They have a lot of guesses, but they can't put their finger on it. But what they do know is it's probably something magnetic. That's what they probably do know. But it might not all be that. Yes, sir.
Yeah, the probe that we sent recently to explore the sun, is that one of the questions they're trying to answer with that probe?
Yeah, Parker Solar Probe. So that's one of the answers. So that probe is amazing, and I think it's already passed a couple times already by the sun. So I don't know how much in depth you want to go into that, but basically that's one of the things is they want to probe the corona, because they're basically flying in the corona. I mean, I think it's less than 10 solar radii, which is kind of the critical zone between where the solar wind goes from subsonic to supersonic. So if you get into that layer, you're really getting into what is actually happening in the corona of the sun. So, and if you're not familiar with that, Parker Solar Probe is this instrument that NASA sent. It was only a couple of years ago when it launched, and it has this huge heat shield in the front. Because you imagine you're going pretty much into the corona of the sun, this very hot place, and the sun is just at your doorstep. It's very hot. So how do you stay alive? How do you keep your instruments at room temperature when you have thousands of Kelvin just shooting at you? And so they built this material. It's basically made out of carbon, a bunch of different carbon layers, and then they have like a plasma detector that peeks out to the front. And then the solar panels, instead of having them out, they actually have to bring them in because there's too much sunlight. So it's kind of like a reverse concept of like International Space Station. They have to hide the solar panels because it's too crazy. But yes, that Parker Solar Probe is one of the things that's going to try to answer some of those questions, looking at the energetic electrons and so on. Yes.
The corona is, like you said, billions of degrees.
Yes, Kelvin. Yeah.
How are they going to get past that?
So it's very hot, but it's very tenuous. So the densities there are very, very, very small compared to like what we're used to like in this room. So that's why it doesn't just burn up instantly. It's because it's so tenuous. So that's actually a really good question because fundamentally, what is temperature? What does it mean to be hot?
Motion of molecules.
Exactly. So it's motion. So, but it's the variation in the motion. Because if you have, let's say you have everything moving together, that's very cold, right? Everything's just moving slowly together, all in the same direction. That would actually be a cold thing. But if the thing is moving, but they're all kind of wiggling around, that would be something that's hot. So when we say something is very hot, what they're actually saying is that the variance in the motion is large. So the idea of how we feel heat kind of changes when you get into very tenuous gases like that, or plasma that's out in the corona. And that's why they can survive, is because the densities are just so low. But at the same time, because the sun is right there, there's a lot of photons coming, and those photons are energy, and they need to absorb that, and that's why they have that shield there. So they can survive in the plasma, but there's just too many photons, so I need to block them out, kind of thing. So, okay. I think my cord is having problems. There we go.
Bills.
All right, so we talked about different lights of the sun, different wavelengths, at least the visible and the UV. And if anybody has any questions on that, please let me know. But I want to start talking about the solar activity and then the solar cycle. So a lot of you probably have been observing the sun, for many years, but I don't know, have you noticed anything about maybe sunspots or solar activity? Does it kind of vary? Is that a thing? Has anybody kind of noticed that over the years? Yeah. And being in an astronomical society, I kind of assume that you probably have more knowledge about the sun than like a typical someone from the public. So I really appreciate that you all have this great enthusiasm about astronomy, as I do, because this is just awesome. So yeah, it's just great. So the sun actually has a cycle that's about 11 years. It's not perfect. It could be 8 years, it could be 14 years, but on average it's about 11 years. And what that activity brings is it brings these active regions where sunspots actually lie. So in this picture they look very bright, but in white light that we would use, there would be sunspots here. So what are sunspots and why are these active regions active, right? Well, sunspots, well, does anybody know like why they're dark? Why are they dark compared to the sun? Why do they look black? Yeah.
Yeah, they're much cooler
Ex-
than around.
Yeah, so why are they cold though? What causes?
Because there's a magnetic field line coming up through them and going down through the other one right next to it.
And kind of suppressing that flow, right? Exactly. So it's kind of so the surface of the sun, if you imagine, you know, boiling a pot of water, you kind of have these convection zones. It's the same exact thing on the sun, except this huge, large scale. You have these convection zones that are rising, bringing up hot plasma, and then they cool and then they settle down. But the plasma carries magnetic field lines. So as they're doing this, they're twisting the lines as they bring this up and as they fall down. And remember, magnetic field has energy, and if you can do reconnection and all that kind of fancy stuff, you can convert it into kinetic energy. So that's kind of the premise of why these regions are so active, is because there's a lot of magnetic energy. There's a lot of tension in the field lines of the twisting and the bending, and that's where basically they get their energies, because of all of this convection motion. And not only that, is you have differential rotation. At the equators, the sun actually rotates faster than at the higher latitudes. So you get all of this just differential flow just mixing up the electric or the magnetic field and causing this activity to pop up. And every so often, this activity affects us on Earth, because those magnetic field lines will reconnect and then they might eject plasma out into the solar system. So before we talk about that, though, I just wanted to kind of go back several decades to show you that this really is a pattern that we have seen. Yes, sir?
I had a question. You said earlier that the velocity is, or the sun rotates at different speeds. Do you mean angular or translational velocity?
So it's kind of like the angular velocity, so like the spin of the sun.
Okay.
So at the equator, if you were able to map a point and then watch it go around until it reaches that same point, it might be, maybe 28 days or 24 days. And then if you go to a higher latitude and you map that point, it might take a little bit longer, maybe 32 days or something like that.
Okay.
But so it's not rigid like the Earth. Like all latitudes of the Earth, they move together as one. But the sun isn't a solid body. It's just a big ball of plasma, and then you have all these magnetic fields, and it has that differential rotation. And that actually helps the dynamo, which controls the cycle in some kind of way. So if we look back, this top panel is showing you sunspots as a function of latitude, north latitude and south latitude on this vertical axis. And then the horizontal axis is time. So as a cycle begins, you have sunspots more or less in higher latitudes. As you can let's look at the next one. You have sunspots in higher latitudes, and then as the cycle progresses, they go down towards the equator until you can kind of see here where the sunspots, there's not very many, and you can see that there's kind of a transition. All of a sudden, the sunspots from the equator just start to disappear, and that's from the previous cycle, and then the next cycle starts and you have them from above. And then the other thing that's not shown in here is that the poles, so the north and the south pole part of the sun, those flip, and you get a change of polarity for how the sunspots are ordered for the north and the south as you go throughout the cycles. But you can see there's several cycles that have been going on. Some are stronger than others. You can see like here in the late 50s, early 60s, there's looks like there was a strong solar cycle. And then the one that just happened, not this last cycle, but the one before, well, this is actually the one we just ended right now. This one was kind of a weak cycle, and they're actually predicting the next cycle to be a little bit weak. I don't know if that's what you guys have heard about that, but that's what I've seen, even at work too, because we actually do some forecasting for the International Space Station for this, so we have to worry about what the sun is doing, because for them, they're flying in low Earth orbit, And if you have a lot of solar activity, that means the sun is a little bit brighter, and it's actually a little bit more brighter like in UV, and that causes the upper atmosphere to heat up. And when you heat something up, it expands, right? So the atmosphere of the Earth, the upper atmosphere expands, and then that gets into Leo, which then causes more drag on the International Space Station. So during active periods of the sun, the space station actually has to boost itself more often than during a solar minimum. So that's why they worry about this kind of stuff. So, and then this bottom panel is just kind of a count, like per year, how many sunspots you've seen. And you can see, it varies quite a bit. And again, these two here, like in the 50s and 60s, there were some pretty decent activity going on there. And then you can see the last one, it was pretty wimpy, right? I mean, this only goes to about 2 counts, and this is up to like 5. So, I mean, there's quite a variation in the strength of different cycles. Okay, so some fun animations. So this is a solar flare that happened on September 6th in 2017. So this was kind of just after the time of the eclipse that I hope all of you saw, right? Everyone saw the eclipse? Okay, good. You guys are awesome. So this was just after that, and I remember I randomly one day I took out my telescope, my solar telescope, and I was like, man, there's some crazy sunspots in the sun. Something bad's gonna happen, because they just looked angry. I mean, sometimes you can just tell from a sunspot, it just looks mad and it's just ready to do something, Sometimes they look really nice and you're like, okay, whatever. But this sunspot looked angry. And sure enough, like a week later, it was just flaring out, X-class flares left and right. And this is a picture right here of one of the flares. I think it was it like an X? I think it was a 10. I don't know. It was a pretty decent. Maybe it was a 9. I can't remember exactly, but it was a pretty decent one. And this was during solar minimum. So we're in solar minimum right now. And a lot of people say, hey, we're at minimum, so we don't have to worry about this space weather stuff. We only have to worry about space weather when the sun is active, when it's during solar maximum, and that's not true. This is a perfect example. This was during solar minimum, and this thing was shooting out X-class flares, left and right, a few of them. And it actually caused, some issues. There was radio blackouts going on. I don't know if anyone's a ham radio operator, but there was blackouts with that.